by Dr. Saeed Jahromi. He will talk about graph-based projected entangled pair state for any infinite lattice. So please start.
Okay, thank you. Hello, everyone. I'm very happy to be here with you, and thanks the organizers for organizing such a virtual event so that we could meet each other. Okay, here today I'm going to talk about graph-based projected entangled pair states. I think it says that my internet is a little bit unstable, but I will switch off the video. All right, so I will talk about graph-based projected entangled pair state, which is actually a generalization of IPEP's algorithm to any infinite lattice in any dimension. So this is a work that has been done in recent years in collaboration with Roman Oros, and also some of the results that I'm going to show you. So I would like to thank him in advance. Okay. So the outline of the talk is as follows. I'm going first to talk a little bit about the contraction schemes that is common for contracting an infinite PEPS tensor network. I will review some of the limitation and challenges, and then I will introduce the graph-based projected entangled pair space, or GPEPS, and give you some ideas how you can resolve some of these challenges to extend the application of IPEP's algorithm to lattices with higher dimension and also arbitrary geometry. And in the end, I will also show you some examples that how this algorithm works in practice, what are its advantages and its limitations. Okay, so I think by now you have heard a lot about tutorials on tensor networks, so I'm not going into the detail. I'm just briefly will comment. Probably you're familiar with tensor network ansatz already. So the tensor network actually provides an efficient representation for the wave function of those systems whose entanglement structure obeys the area law. So you already are familiar in one dimension. One of the famous examples of tensor networks are the matrix productive state, and in 2 and 3 dimensions, the tensor network ansatz is called PEPS, or tensor productive states. So here you would see 2 examples of tensor network, one in 1D and one in 2D, which is the 2D PEPS. The black legs are the virtual degrees of freedom, which carries the entanglement degrees of freedom, and the red legs here are the physical degrees of freedom. So when you have the basically tensor network representation for a wave function, technically you would have a ket, or the quantum state for that wave function. Of course, you would also have the tensor network diagram, or the tensor network representation for its conjugate. And then when you put them together, you can technically calculate the norm of a wave function. So the norm of wave function amounts to the contraction of this network, which if it is an infinite lattice, then it means it is an infinite tensor network, which has to be contracted both along the virtual legs and also the physical legs, which is a challenging problem. Actually, contraction of this network is an NP-hard problem, and it's highly non-trivial and very complicated. So we have to resort to some approximation techniques, which I'm going to review some of them in future slides. So technically, before going to the contraction, we can still simplify this network by building a double layer tensor network out of this. So the idea is that you can technically contract any PEPS, local PEPS with its conjugate along the physical leg, and then join the virtual legs to build a reduced tensor with virtual bond dimension of size d square. And then when you replace it back to the network, you would eventually end with the tensor network, which is now the virtual legs of size of d square. Still, you have to look for some approximation techniques to do the contraction of this network layer. So most of you are already familiar with famous algorithm for approximating the contraction of a tensor network in a systematic way. and controlled way. So boundary MPS technique, a coordinate transfer matrix renormalization group, and tensor renormalization group are three famous examples that have been proven to be very successful in studying many different problems. So in all of these techniques, the contraction and the bound dimension is controlled by boundary dimension chi, which tensors and the boundaries are obtained in an iterative way during the renormalization process, and then the convergence and the computational cost is actually controlled by this boundary dimension chi. So for example, to give you some idea how the boundary MPS technique works, you see here we have a 2D double layer PEPS network with a square structure. We consider one of the boundaries as a layer of MPS, which is amount for the boundary of this system. And then every row of the network is considered as a row of matrix product operator, which is absorbed to the boundary row by row. And then you see that by absorbing this row, we will have increased the bond dimension here. We do the truncation and the renormalization and truncate it back to the dimension chi. And we do this process iteratively until we have convergence on the boundary MPS. So you should do this for all of the boundaries. Of course, if your system is not symmetric. The other way, which is the other algorithm, which is so to say, in practice, it has been shown to be more accurate, is the coordinate transfer matrix renormalization group. So similar to the previous algorithm, the environment around every local tensor basically is approximated by some environment tensor. So here, if you have a local tensor, you would have approximate the contraction of all of the tensors in these corners with some corner tensors, which are these four corners of the network. And then you would also have these edge tensors, which goes to the up, down, and left, right of these tensors. And then you do the iterative absorption of the bulk tensor to the left, right, up, and down, and also obtain these corners so that you have a converged approximation to the environment of this network. And then when you have the environment, you can basically use it to calculate the expectation value of local operators or any other correlations. So, however, as you already saw in these slides, these algorithms mostly works on simple lattice structures like the square lattice that I have been showing here. Aside from the challenges for contracting the environment, we also need some optimization scheme to also obtain the local PEPS tensors by itself. So you have a local Hamiltonian, you apply it on every link of the lattice or every pair of the tensors, and then you have to update the every link of this tensor network so that you obtain a very good representation for the tensor network wave function. However, there are different schemes. So there are simple update approaches, which are based on local singular value decomposition. You update these tensors locally. This scheme does not consider the full environment into account when updating the tensor. So it is fast. It is extendable to generic lattice structure. However, due to lack of full environment in the lattice, it may be inefficient or not accurate enough for some specific problem. The problems that correlation goes beyond the nearest neighbor, the simple update may lose its accuracy. Full update is also another scheme that uses the update of tensor by also considering the full environment and the contraction of the whole tensor network into account. This is more expensive, but of course, this is also more accurate. And on top of these slides, recently there are some ideas how to also optimize and simulate the thermal density matrix system with tensor network, and you can technically approximate the thermal state and study the thermodynamics of these systems or local many-body systems with tensor network. So However, all of these techniques, which are also working, and they are very widespread in the tensor network community, they have also their own limitations. So, for example, for challenges for contracting the environment, techniques like CTMRG, boundary MPS, or tensor renormalization group, they are mostly limited to simple lattice geometry. So, for example, the CTMRG, which is known to be one of the best techniques for approximating the ground state Borg space if you have a tensor network with S-squared geometry. So then it means that tailoring, so to say, a arbitrary tensor network to this algorithm is very difficult. So in 2D, we could still do some fine graining on or coarse graining of the lattice, and then still apply the CTMRG to this algorithm. But extending it to 3D lattices, well, it's very challenging. I think people have already done it for simple cubic lattices, but other complicated 3D structures is still not possible to apply these efficient approximation technique to calculate the environment. And about the challenges for the optimization, of course, the full update cannot be applied to any lattice, especially in 3D and in complicated lattice structure, because you cannot calculate the environment. And also, of course, we could still do simple update, but applying the simple update also to very generic lattice structure is not straightforward, and mostly the techniques which is out there in the market are tailored for simple lattice structure. The graph-based projected entangled pair state, or the GPEPs, tries to resolve the optimization challenges, mostly in this part. However, in this graph-based PEPs, we still have the limitation of the access to the full environment, especially in higher dimensions, like in 3D lattices and in complicated lattice structure. However, it's still, I will show you some evidences that it is working very well for many use cases, and it's a very powerful algorithm for simulating generic lattice structures. Okay, so the main challenge that actually limits the application of tensor network to arbitrary lattice structure and lattice dimension is basically the handling the connectivity information in the tensor network. So the GPEPs algorithm actually uses a clever way to encode the connection information of a tensor network in a matrix, which is called the structure matrix. Okay, so for example, consider you have a lattice structure. I'm showing you here the example to the lattice structure. This is called a star lattice, but the idea is easily generalized to any 3D structure or any other 2D structures. So the first thing you have to do is you have to consider a translationally invariant unit cell of your lattice. It could be of any shape and any size. The only constraint is that it has to be translationally invariant. Okay, and then you could consider this unit cell as a graph. Then you would label every local site as a node of a graph, and then the links of the network, you would call them the edges or the links of a graph. And then using any graph library, it's very easy to basically build the incident matrix of the graph. The incident matrix of the graph is actually telling you which nodes in the graph are connected to each other. So for example, if you look at this matrix, so the rows represent the nodes or the tensors in the graph, and the columns are the edges or the links of the graph. And you would see that, for example, edge 1 here connects tensor 1 and tensor 2. So we have a 1 and 1 here. So it means that there is a connection between them along edge number 1, and the rest of the entries in this column are 0. It means that there is no connection. So the incident matrix already tells you the connection. However, in a tensor network, it is also important to know which dimension of a tensor is connected to which other dimension of the neighboring tensor. So you have to also keep track of the labels of the dimensions. Then you can basically change the non-zero element in every row of the incident matrix, and then label them by the and then replace them by the label of the virtual legs. And so you would see that, for example, here, this structure matrix is obtained from the incident matrix. look at this colorful columns. So for example, edge number 5 is connecting tensor 2 and tensor 5. So you would see that here, edge number 5 actually connects the leg number 4, the virtual leg number 4 of tensor 2 and the virtual leg number 2 of tensor 5. So every column technically give you the information about the connection information in this network. So when you have the full structure matrix, then you can forget about the lattice geometry. You just loop over the columns of the structure matrix and then select pair of tensors along their designated legs, and then you could basically apply the different updates. So here I am going to explain you the simple update, which can be applied to any arbitrary graph. The beauty and advantage of this technique is that then you don't have to carry the burden of the complicated lattice structure. You just have this matrix, and then this is all you need. The structure matrix technically give you all of the information that you need to do the local update with singular value decomposition for the tensor. So suppose that we want to update tensors which are connected to edge number 5. So we have to select tensor 2 and tensor 5. So we have it here, and then it will also, we have these singular values on the bonds, and then we know that dimension 4 of tensor 2 and dimension 2 of tensor 5 are connected, are going to be updated. So we exclude them and keep them for the update, and then we group all of the remaining legs together. We build these MPOs, these MPSs, and then we can do a simple update similar to what you do in 1D for the ITEBD. Of course, here you would see that this group leg, the dimension may be also large. You could also do a subtensor update here and do some singular value or QR decomposition. Consider it as an effective environment, put it aside, and then just use these subtensors to do the update, and you iteratively do this update for every columns of this structure matrix, and then obtain the tensor network representation of the, all tensors in the graph. For calculating the expectation values, so it is very simple. You just calculate the expectation value of local operators like this. The environments are now approximated by these matrices, which contain the singular values. They are approximating, they are somehow they are some mean field approximation to the full environment. Of course, they are not accurate, but if the correlations remain at the level of nearest neighbor for your model, they are very accurate for your problem. So this is how you calculate the single site operator, and this is how you calculate the two-body operators. And then, of course, if you want to increase the accuracy, you could also use the information in the structure matrix and absorb other neighbors into the environment and calculate these expectation values. Okay, so then for this algorithm, for this graph-based algorithm or the GPEPs, all you need is the matrix. Okay, so to simulate a local quantum many-body Hamiltonian on different lattice structures, you just need to build the structure matrix for the units, a translationally invariant unit cell of that lattice. So this idea is generic. It can be applied to 1 dimension, 2 dimension, and 3 dimension on any desired lattice structure. You just need the matrix. So for example, in 1D, this algorithm is technically nothing but the standard ITEBD. However, in higher dimensions, technically, this algorithm amounts to the generalization of ITEBD to higher dimensions. So for example, here you have a 2-side unit cell for the 1D chain. This is the structure matrix that gives you the connection information. If you have a square lattice here, this is the square lattice with 4-side unit cell. This is an example of a structure matrix for such a unit cell. You could also increase the complexity of the lattice structure. This is a triangular lattice. So this is a 9-side unit cell of the lattice, and this is the structure matrix. So you can just use any graph library like in MATLAB or Python to build this structure matrix, and it is very straightforward. And that's it. It's all you need to simulate the local Hamiltonian and this lattice structure. So this is also another example for the Kagome lattice with 12 sides. And this is the structure matrix, and all you need is this matrix. So To go to 3D, these are also examples of the cubic lattice and also pyrocolor lattice. So you would see that you could also simulate complicated lattice structures like pyrocolor. So for cubic is the simplest one. There are attempts for simulating and applying IPEP's algorithm to cubic lattice, and also you could generalize CTMRG algorithm to cubic lattice. However, for these complicated structures like pyrocolor, you would see that extending the approximation techniques for contraction of the full environment is not straightforward at all. However, this graph idea with the structure matrix enables you to simulate also these kind of complicated structures. So these are also other examples of complicated structure. These are the Kitaev lattices that in 2D, this is the honeycomb lattice, example of a Kitaev model on the honeycomb lattice. This is the hyper-octagon, this is the hyper-honeycomb lattices, and these are very interesting structure that Kitaev model on all of these lattices provides examples of spin liquids both in 2D and 3D. And then, of course, it is very interesting and important to be able to apply tensor network to this structure. I will show you some results that shows how we applied the graph-based algorithm for simulating the Kitaev model in both in 2D and 3D on these kind of lattice structures. And of course, this technique has very good potential to also be applied to real 3D crystallographic lattice structure. You just have to provide the unit cell of your crystallographic structure and then build the structure matrix out of it, and that's it. And then you could apply the tensor network to these techniques. So to give you some idea how these techniques is working, this is some benchmark result for the quantum phase transition for the Ising transverse field, both with the standard IPEP's algorithm on the square lattice and the full environment calculated with the CTMRG compared with the result obtained from this graph-based algorithm with mean field environment. You would see that and this is also the relative error, the error compared between the GPEPs and also the standard IPEP's algorithm. You would see that away from the transition point, the relative error is very small, almost zero. However, as you approach the critical point, so this simulation is here, very close to 3 point something. And you would see that when you approach the critical point, so it is natural that in your system, the correlation diverges and goes beyond the nearest neighbor. This is obvious that you would see here that the relative error also increases. However, it's still in the order of 10 to the power minus 3. So depending on the model and the regime of the parameters that you're studying, this algorithm can still be very efficient. And this is also another benchmark result for comparing the energy for the anti-ferromagnetic Heisenberg model on the star lattice. The star lattice is the one that I showed you in previous slides for the introducing the structure matrix. At the regime that JE is stronger than JT on the edges of the star lattice, you would see that how the energies out of GPEPs is compared with different coarse graining algorithm with the standard IPEPs, and there is a very good agreement, which means if you are away from the critical point, the GPEPs algorithm can provide very good result even from the perspective of the energy. Okay. So this was about the ground state. Indeed, you can also simulate thermal state with your algorithm. So you can use ideas from purification to approximate the thermal density operator of a local quantum many-body Hamiltonian. So this is the density operator, and beta is the inverse temperature. This so if comparing the thermal density operator with the standard IPEPs, this is here is a PEPS ansatz, the local PEPS tensor, and this is a PEPS tensor network. However, for simulating a thermal density operator, we would start from the state, which is the infinite temperature state, and then apply the imaginary time evolution on this step, and then do the iteration until we reach the desired temperature beta. So it means that we are cooling down the system from high temperature or from the infinite temperature to the desired temperature that we would like. To do so, the psi of beta is actually a matrix product operator, which is a PEPS with a physical leg and one extra leg, which we call ancillary degrees of freedom. This ancillary leg is actually expands the local Hilbert space of this state. So the full Hilbert space is the tensor product of the Hilbert space of the physical leg and also the ancillary degrees of freedom. And then this purified state is a pure state which can be obtained in this expanded Hilbert state, which we call it a projected entangled pair operator. And then the density matrix is basically is obtained by tracing out the ancillary degrees of freedom. Like here, what is remained, you would see that there are physical legs, which amounts for the Ket degree of freedom, and these are the physical legs which amount for the broad degrees of freedom. You just have to do a standard imaginary time evolution with beta over 2 steps on the some finite temperature state, and then cool down the system to the desired temperature that you like. In the end, when you reach the desired temperature, you would also calculate the expectation value of local operator by tracing over the operator and the thermal density operator of the system. So, and this is how you can technically use the structure matrix, the update, which is very similar to the previous update that I introduced for the ground state. Here, you just only carry the ancillary degree of freedom, and you basically apply the imaginary time evolution gate only on the physical degree of freedom. However, the delta here is half of the delta that you use in the ground state simulation. In the end, after the simulation, you could also calculate the expectation values of local or two-body operators very similar to the ground state case. However, there is this blue legs, which are the ancillary degrees of freedom, which has been traced out by contracting them together. Okay, so and this is how you can use the algorithm to study the thermodynamics of the quantum many-body Hamiltonians on generic lattice structures in generic dimensions. So now I'm going to show you some benchmark results for some of the simulation and the problems that we studied in past couple of years. So this is the application of GraphPEP's GPEP's algorithm for the thermal bosons and 3D structure and 3D lattices. You applied the thermal GPEP's algorithm to Bose-Hubbard model on the cubic lattice and also on the pyrocolor lattice. So here are the phase diagram that you would see here. These are the contour plot of the superfluid order parameters in the these are the Mott lobes. You would see that the superfluid order parameters are 0 in some specific temperature. As you increase the temperature, you would see that these Mott regions basically start to deform, and the superfluid region basically also deforms. And then there are also some normal gas state which emerge in between. It's not obvious in this picture. However, you would see that if you plot it as a function of particle density, you would see that there are regimes that Mott insulator, superfluid, and normal gas in different temperatures can be distinguished with the different order parameters that we can basically measure from our tensor network simulation. So in this normal gas, which are the high temperature phase, the particle density are no longer integer values. You would see that they are deviating from some fixed integer numbers, and then by monitoring these particle numbers, we could basically distinguish these normal gas phases. Okay, and then another interesting problem which we studied both at 0 temperature and also at finite temperature to basically capture the to study the thermodynamics is the Kitaev model on 3D lattice structure. Here is the example of the Kitaev model on the hyper honeycomb lattice. at 0 temperature. So of course, the GitHub model on this 3D lattice structure with trivalent connectivity is exactly solvable. You could do some Majorana fermionization to extract the full phase diagram. However, with the tensor network, we also showed that you could simulate this model and extract the full phase diagram. You would see that if you scan the model or the phase diagram along these lines, which is basically which is in the kx, ky, and kz equal to 2, you would see that you get some peaks in the derivative of energies, second derivative of energy, which basically pinpoint the location of these phase boundaries for you, and you can extract this full phase diagram with tensor network. On top of that, you could also study at the finite temperature properties of the GitHub model on 3D lattice structure and reveal the signatures of fractionalization. So it is very well known that if you look at the specific heat of GitHub model at finite temperature, cooling down the system from high temperature, which you are in a spin disorder phase or in a quantum paramagnet phase, you would first reach a first peak in the specific heat. In this peak is basically amount for the ordering of spins, which is also equivalent to the kinetic energy of Majorana fermions. So it means that the spin degrees of freedom at this first level are fractionalized to both fermionic degree of freedom and also gauge structure. However, still the temperature is high for having a full gauge ordering phase. Then in this region, the Majorana fermions or the spins are ordered. However, if you cool down the system to some low temperature of the order over 100, which is K is the GitHub coupling, then you would reach another thermal phase transition point below which you end up in the GitHub spin liquid phase and the gauge ordering, gauge degrees of freedom orders. Signatures of this transition can be also studied and measured with tensor network applied to this 3D, or the thermal version of this GPEP's algorithm applied to the 3D GitHub on the hyper honeycomb lattice. So this is the first peak showing the spin disorder, so a spin ordering transition, which is here. And it is obtained and evident in the specific heat. However, this is also, let me mention, there is limitation in tensor network algorithm for thermal state based on purification. They have difficulty to converge in very low temperature. So this here, you would see that when we approach very low temperature, we were unable to fully capture this first transition in a specific heat. However, there are signatures of this peak in the bond entanglement entropy that you would see, you could still capture them here and do the scaling with bond dimension to find the location of this peak. So technically, tensor networks are able to also reveal the very important aspect of the thermodynamic properties in spin liquid structures. Another example is the GitHub Heisenberg model, which we scanned the full phase diagram of this Hamiltonia, the GitHub model and the Heisenberg model, perturbed by the Heisenberg model on the hyperoctagon lattice. So setting k equal to sine theta and j equal to cosine theta, you could scan the full phase diagram and extract the spin liquid phases and also the antiferromagnet, zigzag ferromagnet, and stripe regions in the phase diagram very accurately, which is also in agreement with studies based on other techniques. So this is also another interesting study, which we use this graph-based algorithm to study the spin-S, general spin-S GitHub honeycomb model in a magnetic field. So you know that recent studies shows that if you put the GitHub model in a magnetic field, starting and increasing the field, starting from the GitHub region and then reaching the polarized phase in the high field limit, there is an intermediate region which is very interesting, and there are studies suggesting that this region should be another instant of a quantum spin liquid. But of course, there are still some debates. Some people say that There are signatures of a gapless spin liquid, and some other studies based on DMRG suggest a gapped spin liquid in this region. We did this this generic study based on the GPEPs and also with high order series expansion, and extracted the phase diagram of this Hamiltonian for generic spin S with magnetic field. And you would see that this how this intermediate region spreads by increasing the spins. And this is also another example that GPEPs provided very fruitful information about the physics of Kitaev model in the magnetic field. Okay, so let me summarize and wrap up my discussion. So graph-based algorithm is a universal algorithm that you can use for simulating local quantum many-body Hamiltonian on any lattice and any dimension. The connectivity information of the lattice is basically you have to consider a graph which amounts for a translational invariance unit cell of your lattice, and the connectivity information is codified in the structure matrix, and then you can use these structure matrix to do the simple update and update all of the tensors in your network. Of course, in this technique, you have the limitation. The environment is still not as accurate as you like. You have to approximate it with some mean field matrices. But if you are in a regime that you are far away from critical point, or the correlation in your system are not beyond the nearest neighbor, then this algorithm works very good, especially if you are simulating 2D lattice structure with GPEPs. Of course, you could do some coarse graining and or fine graining, and then use your tensors, which are optimized out of GPEPs, and also do the CTMRG. This can be or TRG to calculate the full environment. This is mainly can be done for 2D lattices or simple 3D lattices like cubic. However, for complicated lattice structure, the calculation of full environment is also not possible. And however, another good thing is that while we have we don't have access to the full environment, we're still able to increase the bond dimension locally. So for example, up to 100, it depends on the computational resources that you have. Well, increasing the bond dimension to very large values can locally compensate for the lack of full environment. Of course, it cannot give you information for beyond the nearest neighbor. However, at the local level, it can capture the local entanglement structure very well. So these are the summary of the results, and I think I would like to finish my talk, and thank you for your attention.
Thank you very much.
You're welcome.
Yeah, so now this talk is open for the questions. So first
Sure.
question is given by Wei too.
Oh, thank you. Sorry. Thank you. I have a technical question I want to ask. So,
sure.
Of course, you provide a very good generalization for the complex lattice in the high dimension. But I wonder if the sequence you do the simple update will introduce some, let's say, unwanted bias to the final results. Do you have any comments for that?
So the only unwanted result that we might get out of this algorithm is due to the lack of full environment. So for example, so the simple update for any different for any generic lattice can be done basically systematically without any limitation. The beauty of this algorithm compared to other techniques that uses beta or Husimi lattices is that in this structure you could have also graphs that contain loop structure in them. So for example, on the hyper honeycomb lattice, we have loops that requires like 10 tensors. So we used unit cell of 32 sites, which are very big. So there is no limitation on updating all of these links. However, you might lose some accuracy because you are using the mean field or these lambda environment, and you don't have access to the full environment. So for example, for these complicated lattices like hyper honeycomb, there is no way to, for example, calculate the full environment, at least to my knowledge. So
yes. Yes.
yeah.
For that, I of course I understand. But what I want to probably ask is that, for example, if you can do a simple update according to the sequence of the bound, like E1, E2, E3, dot dot dot. But you can also switch the sequence like E1, E3, E2, dot dot dot. So if you switch the sequence,
you mean sequence of the updating of the edges?
Exactly. Yes.
Well, to be honest, I have never tried to, so to say, update them randomly or in a disordered pattern. I just start from the first column of the structure matrix and do the update and go to the end and everything works. And I don't think there should be any limitation, because technically, when as long as you update all of the legs, okay, I don't think the order of the updates would really matter, because you have to do this in an iterative way until you reach the convergence. All right. I don't. I have never tried this, but I don't think there is any limitation in practice to do this. And in the end, it will not influence your final output results.
I see. Okay. Thank you.
You're welcome.
Okay. So next, Professor Jacob, please.
Thank you for a very nice talk. I have a technical questions regarding if my tensors have symmetries. So how does that symmetry goes in this formalism?
So we have a symmetric version of this code as well. So as long as as long as it is a standard symmetries like U1 or Z2, which the symmetry degrees of freedom are carried on the legs, then there is no difference. You just have to have symmetric tensors. The machinery is exactly the same. However, if you have fermions, then that you have to introduce swap gates, then there is no generic answer how to apply this GPEPS machinery to fermionic systems. We are of course working on that, but currently we don't have answer how to introduce systematically the swap gates in a generic lattice. Okay, so for fermions, there are some concern. However, if you are simulating just, for example, a Z2 symmetry or U1 symmetry, there is no limitation. You could just apply it, because the symmetries are carried along the legs, and as long as you are doing your operation block by block and taking care of the correct symmetry block during the contraction and matrix multiplication and singular value decomposition, there should be no specific limitation in this algorithm.
Okay, thank you.
You're welcome.
Okay, so next, Mori-san, please.
Yes, I have a very naive question. So is this a graph tensor network approach useful for tensor network with internal structure like MERA without reducing it to PEPs?
I would say it is not equivalent to MERA, because the way that you connect the tensors in the MERA is in a very systematic way. The entanglement has to be scaled and basically grows during the branches of the MERAs until they reach the top of the network. But this one, no, this one, I don't think it is equivalent to MERA. It's just a generalization of PEPs or infinite PEPs to any specific or any desired lattice in any desired dimension.
So is this approach applicable for MERA or not straightforward?
Well, of course, yes, it can be also applied. So the idea of a structure matrix can also be applied to MERA. So even in the MERA, you have some connectivity information. Yes, your tensors are connected to each other. You have to know which tensor is connected to which other neighbors along which dimension. So all of this information can also be encoded in the structure matrix. Yes, but at this level, from the technical perspective, how to handle the connectivity information in the network, of course, the structure matrix can be also used for that purpose. But the way that we do the update is not the update that you need for MERA. So for MERA, you have to introduce these disentanglers and other relevant optimizations. But the idea of the structure matrix can also be used in MERA. Yes.
Okay, thanks.
You're welcome.
Okay, so the next, Dr. Chairman Chang, please. So, please.
So I don't hear. Is it any question? So the voice is not clear if someone is asking the question.
Hello, is it better? Can you hear me now?
Yeah, it's not, yes.
Yeah, okay, sorry. So I'm trying to understand better about this, the physical meaning about this mean field approximation of the environment. Does it mean that there's no entanglement between your new unit cell and environment, or does it make assumption of correlation length?
Okay, there is entanglement. So if you have a one-dimensional system like the one that you have in ITEBD, when you split or cut your network in half along any specific leg, then you would be, for example, singular value decomposition. So this singular value decomposition contain the entanglement information, or so to say, they are the density matrix, or the singular values that contain the information about the density matrix. Okay, so this in one dimension is exact. It means that these lambda matrices around any local tensor in 1D is exactly explaining the entanglement to the left and to the right of the tensor. However, there is no theory to prove that this is also exact in 2D. We are extending, so to say, the ideas from one dimension to 2D and higher dimension. We can still obtain the singular values on these links. However, it does not mean that they are exactly basically representing the correct entanglement information when you split your system in half on a bond. That's why we call them mean field, or it is, or so to say, they are providing some approximation to the full environment, but it is not exact. That's why I call them mean field. So at this level, because there is no theory to prove that the singular values by extending ITEB to 2D, they will represent exactly the, so to say, bond information.
I'm sorry, maybe another question. Is this approximation only used in measuring the observable, but not updating the state? Right?
Sorry, could you repeat again?
I mean, is this mean field approximation of the environment, is it only used when you compute the observable, or is also be used in updating the tensors?
It is used in updating the tensors.
Okay,
so basically, when you take pair of tensors, you apply the Hamiltonian to it, and you merge them together. Again, in the end, you have to split them in half, and then retrieve the updated tensors. To split them, you do the singular value decomposition. So these environments are that matrix which contain the information about the singular values. You put them on the bonds. So this is the matrix that that basically carries the singular values out of a SPD decomposition on every bond. Yep.
Okay, thank you.
You're welcome.
Okay, so can I ask one related question? So
yeah, sure.
So can we consider that if we take the large bond dimension limit, the mean field environment becomes exact?
It depends what problem is you are studying. So, well, there is no analytical proof for that. It is problem dependent. However, as long as your correlation remains within the nearest neighbor, okay? If your correlation does not go beyond the first neighbor, this mean field approximation is very accurate, especially if you push the bond dimension to very large. So for example, let me give you some example. Antiferromagnet Heisenberg model on the triangular lattice. In this model, we have geometric frustration. Definitely, there are a lot of quantum fluctuation, and the correlation goes beyond the nearest neighbor. We applied GPEPs to this model, and it does not work very well. No matter how much you increase the bond dimension, it saturates to some value, and then your energy does not go below some threshold, so you cannot reach the best energy that you would expect from other techniques, like from the introducing CTMRG. However, for those models that the correlation remains within the nearest neighbor, it works very well. For example, the Kitaev model, also it is frustrated. However, it is not geometric frustrated. It is the frustration in the Kitaev model is the exchange frustration. The lattice is not geometrically frustrated. The interaction are frustrated. For this method, for this model, the GPEPs techniques works absolutely perfect. And also there are some level of frustration. However, most of the important correlation are remained within the nearest neighbor of the local tensors. That's why we were able to accurately study these models. So it's kind of also depend on your model that you are going to study.
Okay, thank you.
I have a quick comment. Sorry, can I have a quick comment? So
yes,
maybe I don't know how many like a spatial dimension you can go up to, but it seems to me you have a method you can increase the spatial dimension by fixing the bond dimension and see how you can reach the mean field limit. Because we know that at large D, I mean large spatial dimension, you do get to the mean field
exactly
limit.
Yeah.
So
yeah.
I think
Yes.
that's the one thing to worth checking.